Chapter 11, Lesson 1. In this chapter we'll focus on something called intermolecular forces, and we'll take a look in turn at liquids and solids and how these forces affect liquids and solids. So a quick review of the three states of matter. The fundamental difference between the three essentially is the distance between the particles. If you take a look at a gas, the particles are very far apart. There is a lot of disorder. There are no attractive forces between the molecules, so the particles themselves are in a state of chaos, essentially, very randomly arranged and bumping into each other, freedom of motion. In a liquid, there is also disorder. However, the particles are attached to one another, you can say. There are forces operating between the molecules, keeping them together. So they are close together. And in a solid, the arrangement is oftentimes ordered because molecules do not have a freedom of motion about each other. They can't move relative to one another. So there's usually order. Now, the order does not have to be exactly like this. The order itself, the arrangement can be disordered still, but the most important thing is that the particles are in fixed positions. They cannot move past one another, is the idea. The liquid and solid phases are called condensed phases, and essentially that's due to the fact that the particles are attracted or attached to one another. Now here it says the state of a substance depends on two factors, two antagonistic entities: the kinetic energy of the particles, one, and the strength of the attractions between the particles. So if you have, say, three pieces of matter at room temperature, a solid, a liquid, and a gas, all of them have the same kinetic energy because they're at the same temperature. However, what decides which one's a liquid, which one's a solid, which one's a gas, is the attractions between, the strength of the attractions between their individual particles. So this is also another review. Feel free to take a look at this, but you should be familiar with the fact that gases are compressible because the particles are far apart. We talked about diffusion. Liquids can also flow because particles are free to move around each other. Diffusion also occurs with liquids, and with solids, since they do not flow, and diffusion technically is extremely slow, or in most cases we don't even talk about solid particles diffusing. And so this should be a summary of liquid gases and solids. So the big talk will be about these intermolecular forces. Now we have to distinguish between intermolecular forces and intramolecular forces. The force that we'll be studying in this chapter is this force that attracts two molecules together. Now the force within a molecule, this here is a chemical bond. And in order to break it, you'll have to undergo a chemical reaction. Whereas this force, we can say, is a physical bond. Now these are good ways of thinking about them. There are cases in which chemical and physical bonds really cross between the two much more easily. But in general, we'll be taking a look at the forces between molecules, and these forces will influence properties such as boiling points and melting points and viscosities and the like. So these forces, even though they're weak, so this force right here is weak compared to the covalent bond, which is strong. That's why anytime you heat up a substance, usually you are breaking apart this force. You're essentially boiling a substance and separating the molecules from one another. In order to separate the atoms within a molecule takes much more energy and has a totally different type of reaction. So the forces that we'll be dealing with essentially are in general called van der Waals forces, and this is named after a famous scientist by the name of van der Waal, most likely somewhere from the European continent. So there will be three of these that we'll talk about in turn: dipole-dipole interactions, something called hydrogen bonding, and then something called London-dispersion forces. We'll take each three of these in turn, but recall all of these are intermolecular intermolecular, between molecules. You have one molecule, you have another molecule. The force of attraction between these molecules is what we'll be dealing with. Very important. The first one we'll take on is the dipole-dipole interactions. The first thing to do then is to recall that the word dipole means you have yourself a polar molecule. So molecules that have permanent dipoles are technically polar, which means they have a positive end and they have a negative end. And the positive end is attracted to the negative end, is the idea. And here it says these forces are important when the molecules are close to one another, which makes sense because if the molecules are far apart, this force is too weak to be felt between the molecules. But it does increase or comes into play when they come close enough together. I think of it kind of like magnets. Two magnets, even though they are attracting each other, unless there is a minimal distance between them, they will not smack together into each other. So these dipole interactions, you can say, kind of look like this. And remember, this is between molecules that are polar. So if you have yourself a polar molecule, you have a positive end and you have a negative end. And these two essentially cause, this polarity difference is what causes these intermolecular forces. And the interactions right here between the like charges will repel, interactions between opposite charges will attract. So overall, the attraction wins and the molecules coalesce together into, say, a liquid or a solid. So if you take a look, here is the dipole moment. This is essentially a measure of the strength of the polarity of the molecule, how polar the molecule is. You'll take a look at, if you take a look at acetonitrile, which is very polar, has a very high boiling point, which means the particles have strong forces keeping them together, whereas propane has similar molecular weight, 44, 41, actually a little heavier, but the polarity is very, very low. We can say it's nonpolar, and it is has a low boiling point. This is quite a bit below 0 degrees Celsius, so negative 40 or so. So propane is a gas at room temperature, is the idea. So the polarity essentially has a very important role to play in determining the physical properties. Remember, these physical properties, essentially, in order to cause a substance to boil, you have to break this bond that's keeping the molecules together. The second one we'll talk about is London-dispersion forces. We're going to go a little bit into detail of what this force is, and we're going to do it by analyzing a helium atom. Now, the reason we use helium is because helium is the lowest boiling substance. It boils just a few degrees above absolute zero. So, but even so, helium can be made into a liquid and indeed into a solid. So helium has 2 electrons. It has 2 protons, 2 electrons, and here it says the electrons in the 1s orbital of helium will repel each other, and here it says tend to stay away from one another. So these are the 2 electrons. Usually they repel one another. It happens sometimes, occasionally, that they wind up on the same side of the atom. So in this case, the electrons wind up on the same side of the atom, and this will give the atom a slight negative charge. So this is essentially the picture that you see. You get both the electrons essentially on this side of the atom. And what we have then is a shortage of electrons, so a slightly positive charge on this side and a slightly negative charge on this side. So what happens is this atom of helium actually acquires the same picture as a polar molecule does for an instant, you can say. Then another helium nearby will be affected by this arrangement. Since you have 2 electrons on the left side, the next atom, if they come closer enough, will induce, this atom will induce the same picture in the next atom, is the idea. So the second helium atom will get the same picture. These electrons will technically arrange themselves or go to the opposite sides of the atom. And you get yourself an arrangement like this. Now both atoms of helium have the same picture. So you get yourself the positive and the negative side on both sides of them. And now an attraction forms between them, is the idea. So these London dispersion forces, the reason we call them dispersion forces is because they arise from the dispersion of electrons in an atom. This is between an instantaneous dipole and an induced dipole. Instantaneous, that was our first helium atom that instantly, for an instant, got the electrons to be essentially on the same side. And then the induced dipole is this atom then induced or created the same sort of picture in its neighboring atom. Now, it's important to say that these forces are present in all molecules, regardless of polarity. So if a molecule is polar, it has permanent dipoles in it, but it also has this temporary dipole or instantaneous dipole in it. And how well the electron cloud can do this sort of thing can end up on the same side, you can say, is something called polarizability. So we can talk about how polarizable is the molecule. The more polarizable it is, that is, the easier it is for the electrons to get distorted, the stronger this instantaneous dipole that gets created. So an example of this is the shape of molecules. If you take a look at the shape, there are two molecules. Both of them are actually exactly the same formula. Here you have N-pentane and neopentane. Both of these are actually C5H12. Now, that's 5 carbons and 12 hydrogens. Depending on how the carbons and the hydrogens are arranged, you get this different idea of polarizability. So, because a long molecule is can undergo more polarizability than a spherical molecule, that is, electrons can end up more on one side than on the other, this molecule actually has a higher boiling point, which means it's the strength between its molecules, the force between its molecules is stronger. And this idea of polarizability, it's easier to get the electrons on one side, you could say, than it is on the other. Whereas with a spherical molecule, that still happens, but not to the degree as it does in a longer molecule. If you take a look overall at the molecular weight, you can see that the higher the molecular weight, the higher the boiling point. Here we're looking at the halogens, the diatomic elements in group 17 of the periodic table, and you'll see the heavier the molecule gets, the higher its boiling point, which means the stronger the forces between the molecules. And this essentially is because there are more electrons on the atom. Iodine, for example, the atom iodine is very big compared to the atom fluorine, which means the electrons can actually polarize much more easily on iodine than they can on the fluorine. You can see the exact same idea in terms of the noble gases. Now, all the noble gases are gases. There's no liquid, but you can still see the trend. Here, helium just 4.6 degrees above absolute zero, but xenon, is quite a bit above absolute zero here. So the molecular weight, the higher the molecular weight, the higher the boiling point, because the stronger the dispersion forces. Even though, remember, the molecular weight essentially is a measure of the mass of the nucleus, whereas the electron cloud is the one that causes this dispersion. But the higher the mass of the nucleus, the more electrons you have in general. That's why this trend is easily seen. So the question is, which has the greater effect? Is it more important to have a higher polarity, or is it more important to be bigger in terms of your electron cloud? Well, here it says if they are of comparable size, then the dipole interaction will win. It'll be the dominating force. If one molecule is much larger than the other, then dispersion forces will likely determine the strength of the bonds and therefore the physical properties. So really, we'll take a look at this in a few examples here, but it's important to keep both of these ideas in consideration. And then we're going to come up to the third intermolecular force. The third one we're going to show you why we consider the third one to be very important. So here what we see, what we see here is a graph of group 14 compounds. So you have carbon, you have silicon, germanium, and tin as you go down the periodic table. And if you graph their molecular weight against their boiling points, what you see is that it steadily increases, which is to be expected. We said the higher the molecular weight, the more electrons you have, the higher the boiling point. However, if you compare the same thing with group 16, so these are group 16 elements, oxygen, sulfur, selenium, and tellurium, you see a big anomaly. You see that water has a very strange, a very high boiling point, which means the strength of the molecular force between the water molecules is much stronger than between really anyone else in the group. And this is very curious and puzzling. So water has something in it that completely throws it off course. It's something that creates very strong forces between the water molecules. And this is due to the fact, or due to something called hydrogen bonding. Now, hydrogen bonding is a very important concept, very important intermolecular force. What happens is anytime hydrogen is bonded, chemically bonded, to either nitrogen, oxygen, or fluorine, what happens is you have a very unbalanced distribution of electrons. And this is true of these three. Essentially what happens is these three, nitrogen, oxygen, and fluorine, the three most electronegative elements on the periodic table, pull the electrons off of hydrogen so much that hydrogen's nucleus essentially gets exposed. And it's a little embarrassing, but if you have yourself, say, OH, an OH bond, remember that hydrogen is simply one proton, one electron. So when oxygen pulls the electrons off of hydrogen, the hydrogen nucleus effectively is laid bare, and creating a very strong positive charge on the hydrogen. And that's essentially where this comes from. And then the hydrogen, having such a strong positive force on it, is then attracted very strongly to the negative side of a neighboring molecule. This is what happens in the case of oxygen. The hydrogen, positive hydrogen, exposed positive hydrogen, is attracted to the negative side of the oxygen of a neighboring molecule. So these are called hydrogen bonds. Hydrogen bonding essentially is the strongest of the intermolecular attractions. It is so strong that very often it comes close to being almost like a true chemical bond. And this is essentially the reason for why ice, ice forms these expanded crystal structures in the solid phase. So we all know that ice cubes float in water, and the idea here is as the molecular motion causes these molecules to come together, the strength, the enormous strength between the molecules causes them to align in a certain way. And this alignment essentially expands the structure, creating a less dense structure in the case of ice, and this is why ice floats. And the hydrogen bonding in water essentially is what partially explains why ice is less dense than liquid water. Now, and here a little more explanation of, I think we just talked about, the hydrogen nucleus technically is exposed. And this happens with the three most electronegative elements. If you recall, in the periodic table, you got fluorine, oxygen, and nitrogen as the three most electronegative elements on the periodic table. And you got yourself carbon, and so on and so forth. But these three are the most electronegative, highest electronegativity. Lastly, we'll talk about something called ion-dipole interactions, and this is essentially, you can say, a fourth type of force. And this happens whenever you have yourself a dipole, that is a polar molecule, and a truly ionic compound. So the reason why, for example, salts like sodium chloride are easily dissolved in water is because water is a very polar molecule having a partial negative, a partial positive charge. Salts are fully charged particles or compounds with a full positive, full negative charge. So these two can interact. And the reason why water is such a great solvent, that is, it can dissolve many substances, is because water has such a high polarity. Essentially because of hydrogen bonding. So water is actually very good at dissolving many salts, many ionic compounds. Apologize. So we're going to finish this with a few examples. Here it says the dipole moments of methyl chloride, CH3Cl, and methyl iodide, CH3I, are 187 and 162 dBi. This is a unit of polarity, measures the dipole moment. A says, which of these substances will have the greater dipole-dipole attractions among the molecules? Well, because the polarity of CH3I is higher, the polarity of CH3Cl is higher. And this one, if we take a closer look, this one may be a bit, let's make sure we align them. So CH3I, this is the same, methyl iodide has a polarity of 1.62. So, and then CH3Cl has a polarity of 1.87. So because CH3Cl has a higher polarity, it will have stronger dipole-dipole forces, is the idea. Which will have greater London dispersion attractions for part B? Well, because iodine is quite a bit bigger than chlorine. If you take a look at the periodic table, you get yourself fluorine, chlorine, bromine, and iodine. Iodine is 2 levels below chlorine, so quite a bit bigger. Iodine then will have greater dispersion forces. So you get CH3I will have greater dispersion forces. And then C says the boiling points of these two. Let's go ahead and circle them again. CH3Cl is 249 and CH3I is 315. So these two are connected and these two are connected. Which substance has the greatest overall attractive forces? Well, because the boiling point is greater in the case of CH3I, it therefore has the greatest overall attractive forces. So what we can see is that London dispersion forces have 1. So London dispersion is more important here. And it's essentially due to the fact that iodine is a very big molecule compared to the chlorine. That's the idea. Why don't we try another one? In which of the following substances is hydrogen bonding possible? So remember, hydrogen bonding is this third. You can think of hydrogen bonding as a very severe case of dipole-dipole force. It occurs because the hydrogen bonding molecules are very, very polar. You can think of it that way. So if you take a look at methane, if we draw its Lewis structure out, what happens is you do not see hydrogen bonding here, because remember, hydrogen bonding, you have to have oxygen, fluorine, or chlorine bonded together to hydrogen, and here there is no bonding, so no for this one. If you take a look at hydrazine, we also will have to draw the Lewis structure of hydrazine, and it's better to be careful here. So we have from nitrogen, each has 5 valence electrons. Then we have 4 more hydrogens, so we get a total of 14. And let's go ahead and put the 2, 4, 6, 8, 10, 12, 14. That should work. Now in this case, there is hydrogen bonding possible because you have a very electronegative element, nitrogen, bonded directly to a hydrogen. So because this is this will work. So we can put yes on this one. How about CH3F? Now it looks as though the hydrogen and the fluorine are present, so this should work because fluorine is a very electronegative element. However, the way it is attached, if you take a look, is the hydrogens are actually not directly on the fluorine, and because the hydrogen is not directly on the fluorine, there is no hydrogen bonding possible. In fact, so the CF bond does not create hydrogen bonding. Remember, it has to be hydrogen, which is essentially one proton, 1 electron that this works with. And then finally, H2S will not happen in H2S because you don't have the 3 necessary electronegative elements, so it does not happen in this one. The only one it happens in is this hydrazine molecule for hydrogen bonding. And then finally, we'll end up with example 3. Here it says list the substances barium chloride, hydrogen gas, CO, HF, and Ne in order of increasing boiling points. And recall, this is a measure of how strong the attractions between them are. Now, if we analyze this, we automatically see that we have ourselves a salt. Now, anytime you have a salt, you have positive and negative charges, fully positive, fully negative charges. In the case of barium, we have a +2 charge, so this creates a very strong attraction. So barium chloride should definitely be last, with the highest boiling point. At the lower end, we have the two smallest ones are neon and hydrogen. Now, if we think about these, CO is polar, because you have two different elements attached. Hydrogen fluoride is also polar, whereas neon is just an atom, and hydrogen is also nonpolar. So what we see is neon and hydrogen will probably be first, and then carbon monoxide and HF will be second. Now, in general, HF should be right next to barium chloride because HF, recall, has hydrogen bonding in it. This is because of H bonding, because hydrogen bonding is the strongest of all the intermolecular forces. So HF goes right next to barium chloride. The next would be carbon monoxide, since it is polar. You can say because polar. And then between these last two nonpolar species, we should put neon as next, because larger electron cloud and stronger dispersion forces, larger electron cloud, which creates bigger dispersion forces. So finally we get ourselves hydrogen to be the first in this order. Hydrogen is the second lowest boiling substance right after helium. So this should be the arrangement here. And again, we're arranging them in terms of the strength of their intermolecular forces. So this should conclude for us, I believe, lesson 1 of chapter 11.